Let's take a look at the solution of this polynomial inequality. We have x minus 3 whole thing squared times x plus 1 less than or equal to 0. You may have solved inequalities before that didn't have a square like this, and so the introduction of the power adds a little twist to this problem, and let's work our way through this. So we have these two factors, x minus 3 and x plus 1, and those should give us breakpoints. And those breakpoints occur when x is either equal to a positive 3 or when x is equal to a negative 1, setting each of those factors equal to 0. Next, we'll use the breakpoints to divide up the number line. So here we've got the number line with breakpoints at positive 3 and negative 1. And from these two breakpoints, we get three regions for this number line. So the first region is values where x is less than negative 1. The second region is for values when x is between negative 1 and positive 3. And then the third region occurs for values which are greater than positive 3. Now that we have the regions, we're going to test each of these regions for the original inequality. When we look at the inequality, x minus 3 whole thing squared times x plus 1 is less than or equal to 0, we'll plug in values of x that appear in each of the three regions. So for example, in region 1, something that's less than negative 1, I could pick x is equal to negative 2. And when I plug this into the inequality, the actual numerical value isn't important, but what I am concerned with is what is the sign of each of those factors. So when I plug in the number negative 2 minus 3, that comes out to be a negative number. But then I'm going to square that. From the second factor, x plus 1, I have negative 2 plus 1 is a negative number, and this will not be squared. And now I want to determine, is this less than or equal to 0? When I square this negative number, it becomes positive. Positive times negative is a negative number. And a negative number is less than or equal to 0. That is a true statement. Next, I want to move to region 2, those values between negative 1 and positive 3, and x equals 0 fits into that region, so I'll choose that point. When I plug it into the inequality, 0 minus 3 is negative 3, which is a negative number, and I'll square that. The second factor, x plus 1, if I put in 0 plus 1, that becomes positive 1, which is a positive number. And we're testing to see whether this expression here is less than or equal to 0. When we look at the square, a negative sign squared becomes positive, and then multiplied by a positive number is going to be positive. And when we compare that to our inequality, which says some positive number should be less than or equal to 0, that's actually false. Positive numbers should be greater than or perhaps greater than or equal to 0. So we mark that region as false. Next, we move on to region 3, choosing a point that's greater than 3. We could pick anything, x is equal to 4 or 5. Again, we're primarily concerned with the signs, not the numerical values. So when I put in positive 4, 4 minus 3 is a positive 1, and I'll square that, and I multiply by 4 plus 1 is a positive 5, so I'm multiplying by a positive number. And then when I test to see whether this is less than or equal to 0, what I'm seeing is positive times positive, again, is positive. And so when I mark whether that's less than or equal to 0, that also is false. So we go back and we take our markings and shade the region or regions that are true. And in this case, the only region where that applies is region number 1. So I'll shade this. And while we know that the points within this interval are true, we also need to test the breakpoints, which include not just the endpoint of this interval, but also the breakpoint which appears when x is equal to 3. So let's go back and test those 2 points in the original inequality. And when I plug the point x is equal to negative 1 into the original inequality, I get that -1 minus 3 whole thing squared times a -1 plus 1 less than or equal to 0. And we can see that this factor becomes 0. And because there's an equal to symbol here, the point 0 is included. And so 0 less than or equal to 0, that is true. So I will say that the point at -1 is included, and I'll indicate that by putting a square bracket on the end of this interval. However, I also have to test the point where x is equal to 3. And when I plug that into the original inequality, I get 3 minus 3, which gives me a factor of 0 raised to the second power, and then I don't really care what's in here, because I know that this factor is going to be equal to 0. And is that less than or equal to 0? And yes, that product again is 0, but 0 less than or equal to 0 is also true. And what that means is that I have a single pinpoint at x equals 3, which is true, so I'm going to shade that in, even though the surrounding regions are false on either side. So I have a kind of unusual solution. The first part of the solution is an interval. It's the interval between -infinity and a -1, with the point at -1 included, so we use the square bracket. However, I'm going to also include, so put union, with the single pinpoint, and that is just the single point at +3, and so I use the set notation to include just a single point, and that is the solution for this inequality. The subtlety of this problem is introduced with the square on the factor, and as you can see, whenever you square the factor, you cause the signs to be positive, and so if there had not been a square, we would have expected this region to be negative. And if this region had been negative, the pattern on our regions would have been true, false, true, which is more typical of what you may have seen previously. Sometimes with an unusual pattern where there are two false regions or two true regions that are adjacent to each other, people forget to test the breakpoint which falls in between the two regions, but we need to do that. And in this case, we did see that there was that single point that appeared because of the less than or equal to sign from the inequality. In a different problem, it would be possible to have two true regions, but if there were an inequality without an equal sign, that the breakpoint in between the two regions is false, and that would give an interval that had a point missing at that breakpoint. So in general, there are all kinds of weird and wacky things that can happen when you introduce an exponent on one of the factors, especially if that exponent is even.